By the middle of this century, the global transition to electric mobility will put an estimated 1.65 billion battery-powered vehicles on the road. This diagram shows the core mathematical problem of that transition. If those 1.65 billion vehicles all plug in to a standard 7-kilowatt charger at the end of the workday, they generate a sudden demand of 11.6 terawatts. To put that in perspective, 11.6 terawatts is more than 3 times the total electrical generation capacity of the entire planet today. Hitting the current power grid with that level of unmanaged demand would trigger rolling blackouts, melted transformers, and catastrophic physical failures across the transmission infrastructure. Preventing that collapse means we can no longer treat chargers as passive electrical outlets. They must function as active, intelligent nodes in a digital network, negotiating power in real time. Solving this grid paradox and guaranteeing that any car can charge at any station requires a highly standardized technology stack. The lower half of this system is governed by physical standards. These are the literal hardware connections and cables that safely manage raw electrical transfer. The upper half is governed by communication protocols. This is the software dictating digital authentication, encrypted billing, and the dynamic load balancing that keeps the grid stable. To understand the modern electric vehicle landscape, we have to build this architecture from the ground up, tracking exactly how electricity, data, and capital flow through each distinct layer. The foundation of the entire system is the physical connector. This is where the electrical handshake between the car and the station actually happens. At this level, the engineering parameters are strictly physical. The standard dictates the exact shape of the plug, the layout of the pins, and how the electrical phases are mapped. For years, the industry relied on base-level AC standards, like J1772 in North America, which are highly effective for slower, single-phase residential and public charging. This diagram shows the next major evolution, the Combined Charging System, or CCS. It retains the upper AC section for everyday use, but adds 2 heavy DC pins below it. Those dedicated DC pins bypass the vehicle's internal AC to DC converter entirely, pushing hundreds of kilowatts of direct current straight into the battery. But even with CCS, physical standards remain regionally fragmented. North America adopted CCS1, Europe standardized on CCS2, and China developed its own GBT connector. We are only now seeing a market shift toward unified hardware, most notably with the rapid cross-brand adoption of the high-power NACS connector. Yet, a unified physical plug only guarantees that electricity can safely cross the gap without causing a fire. The hardware itself lacks the intelligence to authorize a user, bill a credit card, or negotiate power limits. That requires a digital software handshake to accompany the physical connection. This local data exchange, executed directly between the vehicle and the charger, is governed by a protocol known as ISO 15118. This schematic illustrates the protocol's most visible feature, plug and charge. The vehicle and the charger use embedded digital certificates to verify identity and approve billing automatically. This removes the need for the driver to open an app, scan an RFID card, or swipe a credit card. Authorization happens the moment the cable clicks into place. But the most critical capability comes with the updated ISO 15118-20 protocol. It enables bidirectional charging, allowing power to flow backward from the vehicle's battery through the charger and into the broader grid. This vehicle-to-grid mechanism directly addresses the 11.6 terawatt threat. It transforms millions of parked cars from a massive drain on the system into a distributed network of stabilizing battery storage. Local communication makes a single charger highly intelligent, but as long as it operates in isolation, it can't coordinate with a commercial network. To function at scale, that local station has to report its metrics back to a central management system. This network topology maps the Open Charge Point Protocol, or OCPP. It serves as the standardized backend language between the hardware and the operator server. OCPP handles a constant stream of real-time data packets, executing firmware updates, sending control commands, and reporting session metering. By using a universal language, OCPP dismantles hardware vendor lock-in. Any compliant charger can be installed and managed by any operator software. That leaves one final gap in the ecosystem, allowing a consumer who subscribes to one network to seamlessly roam and charge on a competitor's hardware. That gap is closed by the Open Charge Point Interface, or OCPI. This protocol bridges disparate networks to enable roaming and tariff exchange. OCPI operates strictly cloud to cloud, coordinating live pricing and availability data between the company operating the physical charger and the e-mobility provider managing the consumer's account. This three-tier stack perfectly solves the engineering and logistical challenges of global charging. But an open standard is only effective if corporations actually use it. For years, the voluntary adoption of these protocols left the landscape highly fragmented. Drivers face dead zones, incompatible plugs, and a mess of proprietary apps that delayed cross-border travel. To force compliance, the European Union passed the Alternative Fuels Infrastructure Regulation, or AFIR. This legislation acts as a brute force catalyst, mandating the aggressive deployment of public charging stations with strict enforcement deadlines in 2025 and 2027. This map shows the immediate spatial requirement. Fast charging hubs must be constructed every 60 kilometers along the Trans-European Transport Network. Each node must guarantee 400 kilowatts total capacity and include at least one connector delivering 150 kilowatts. AFIR removes the option of private walled garden networks. It forces the transition of EV infrastructure into a highly regulated, standardized public utility. The regulation also targets payment fragmentation, systematically dismantling proprietary subscription models and exclusive operator applications. It mandates universal ad hoc payment access, requiring immediate, contactless card interactions directly at the hardware. Under the law, all newly installed public chargers with an output over 50 kilowatts must integrate physical point-of-sale card readers or NFC technology. For AC chargers and DC units under 50 kilowatts, operators must provide uniquely generated dynamic QR codes to process secure ad hoc payments without an app. It also enforces strict data transparency. The total price per kilowatt hour must be clearly displayed to the user before the electrical session even initiates. On the back end, AFIR requires operators to maintain open APIs, publicly broadcasting their static location data and real-time operational status to monitor the health of the grid. By legally fusing universal hardware with open communication protocols, AFIR ensures that electric vehicles will operate not as isolated machines, but as critical interoperable anchors for the global energy grid.